Okay. Okay. Uh, my wonderful students. Sorry I was a little bit late coming through the rain, as all of you were. So, a couple things I want to make note of with you. Uh, Yesterday I revised and updated the clicking data for lectures 5, 6, and 7. This is lecture 8. The end of our fourth week of classes. And some of you may have noticed that you're clicking answers and clicking correct numbers may have changed. And that is because there was a problem with one of the formulas that in the spreadsheet I was using that is now all straightened out. Everybody should be correct and up to date. This is what the participation rate looks like for both sections, this section and the morning section. We have a total enrollment of 582. Right now, out of the 6 questions that I have asked for the last 3 or the previous 3 lectures, 343 out of 582 have answered all 6, and that is good. Now, 100 out of the 582 have answered 5 out of 6. And then there's dribs and drabs. And there's 34 students that are not on the scoreboard at all. They have 0 answers. And that is not so good. I know some of you are still, fighting your financial aid and stuff. So it's getting late. And so if you can't get it done for next week, it's going to start really hurting your grade. But these guys up here, they are looking good for 25 out of 25 if I were to do semester grades today. But we still got another 3 months to run. So we're not going to be getting close to the time until the end of November, so Thanksgiving. But if I were to do grades today, these guys would get 25 out of 25. Then 5 out of 6, that's 83.33%. So that's below 85%. These guys down here, 100 people, I would have to calculate based on the 85% factor. So if you're above 85%, it's just 25 points. You get them all. Below that, you have to calculate. But I want to go another week or two before I give you an example of how the grades calculate for these guys down here. Because right now it's kind of boring. But in a few weeks, we'll have students, we'll have about 20 questions on the books, and we'll have students that are scattered a little bit more indicatively. But most of you are here in 6 out of 6 territory, and that is where you want to remain in the 100% participation category, and most of you will. And so a few of you will maybe be a little bit below 100%, but almost everybody is going to be above 85%, so don't worry about that. It's still early days, and like this guy here, 4 out of 6, that's 66%. There's not going to be many of you with 66% participation at the end of the semester. Everybody's going to be way up there. So it doesn't look that interesting right now, but I will do an example of this with you in class directly sometime after exam 1. And then we'll have plenty of questions on the books. Now, we're going to have some clicker questions today, so you may as well get them out. I want to recap some of the conversation we had concerning Aristotle and Galileo and that mythical frictionless plane, the horizontal plane, and the Ferrari that we drove off the cliff at a constant speed of 20 meters per second. Now, Mr. Aristotle from Greece would have said, hey man, if that thing is moving, even if it's a constant velocity, there's got to be some push acting on it. That was his approach. And it's not, it's not, he was wrong about that, but it's definitely understandable that he would make that point about motion. Galileo was able to say, no, man, if it's at constant velocity, there's no, you don't need a push force to keep it at constant velocity. It'll do that on its own. And Galileo was able to prove it geometrically. Now, I want to go over that geometric proof again with you, a little bit slower. Let's see if we can put it back together, similar to what's in the textbook. So this will reinforce your reading in chapter 2. So let's simplify the argument. We'll talk about a 1 kilogram object. So that's like a liter bottle of water, give or take a gram or two. And we're going to say it's going at a good, nice, even 1 meter per second, 1.00 meters per second. And let's say that this object has some generic unit of force. Now, we're not saying metric units of force just yet, but some generic unit. We'll say it has 1. 1 unit of downward weight force. And in the diagrams yesterday and in the textbook, I used the symbol W, capital W, for that weight force. Okay, downward, capital W for weight. And so let's say that this object, if it has 1.00 generic units of force downward from the weight pull, from the gravitational pull of Earth, then what that also means is that you have to push it upwards by the same amount of force. So if you exert 1.00 generic units of force upward, you'll balance it out. You'll support it. It'll be stable. Okay, and that was the upward vector in lecture and in the textbook labeled capital Y. Right, so this is our simplification. Now let's get back to this dialogue between Aristotle and his student Galileo. The student has become the master. Galileo is now the master of Aristotle. And I'm sure Aristotle, if he were still alive, he would say, you get it. You go, Galileo. So here's Aristotle again making his claim. Now this one's in terms of the simplification that we just looked at. And so here's what Aristotle would have said. That liter of water needs a small push. And Aristotle says it needs 0.100 generic units of push. Even on the mythical frictionless plane. All right. That's what he was saying. He had this idea that if it was moving, something had to be moving it actively. It wouldn't just move and stay in motion on its own. Right? So if it's moving at 1.0 meters per second, he said there's going to be some little unit of force, and we use the label P, lowercase p, for that force. And Galileo said, no way, Jose, because 0.100 generic units of force, hey, I got a ramp that's the downward force on the ramp. So if you tell me you need if you tell me that you need 0.100 units of force on a horizontal, Galileo says, no, that's not right. That's way too much, because that's what you need on a ramp. And he said, I can even build the ramp for you and show you. He backed up his claim with action, with something that he could construct geometrically. So here it is. This is a little version of it. And we're going to blow this up in just a second. But first we got a question here. Capital D is the force going down the ramp. Remember how last time we said, if your ramp is vertical, you don't really have a ramp. all of your weight force accelerates you along that ramp. But if you tilt the ramp so it's slanted, you get a little bit of force down the ramp, but most of it's being absorbed by the ramp. So you have some along the ramp and some perpendicular to the ramp, okay, depending on the tilt of the ramp. And Galileo was saying, I know how to get that down ramp fraction. It's just, proportional triangles, which we did last time. And here it is. I mean, he said, look, if this thing has a weight force of 1, and you're saying that on the horizontal it needs 0.1 units of force, then I say, let me build a ramp of this proportion, where the hypotenuse is 1 unit of distance, and the height, the altitude, is 0.1 unit of distance. Okay, so the forces that Aristotle claims tell Galileo how to lay out his ramp. And he said, if you do that for this 1 kilogram object that has a 1 generic unit of force weight, then the down ramp fraction of the force, because on this ramp it's going to be like this, You're going to accelerate, but it's not going to be 9.8. So that the fraction of that acceleration that you get, the fraction of the full weight force down the ramp is basically computed this way. All right? And so Galileo says this ramp gets 0.100 generic units of force to propel it down the ramp. So you don't need that. That's way too much for horizontal. Horizontal, whatever you find for a ramp, the horizontal is going to be less than that. All right? So if you tell me that 0.100 is what you need on horizontal, I can make this ramp and say, no, wait a minute. 0.100 is what you need for this ramp. It's not what you need for the horizontal. Whatever you do, 0.100, that's way too much for horizontal. And no matter what number Aristotle said, all right, Galileo, so 0.100 won't cut it. Let's cut it down to 0.010 units of force. And Galileo would have been able to say, I got a ramp for that. And so Aristotle's, all right, okay, I get the ramps. Let's just go down to 1,000th of a generic unit, 0.001. And Galileo would be able to say, oh, I got a ramp for that. Aristotle, Ari baby, whatever you give me, I can build a ramp. And basically, you're out of here, Aristotle. I'm the master now. And Galileo was able to prove basically that there is no minimum value for pushing any object on this horizontal ramp. It'll just keep going. It doesn't need any newtons of force. All right? Any positive number is too much. And therefore, on the ramp, to keep going, it needs exactly 0 on the horizontal plane. And that, my wonderful students, is actually Sir Isaac Newton's first law of motion, which we will tackle in just a few minutes. But before we do that, I want to look at a few more ideas related to the reading and to the homework. So take your clicker out, and we're going to click through some questions, starting with some multiple choice, and then we're going to do some numeric and some alphanumeric questions. So hold on to your hats, because here we go. Question number 1. And by the way, this is frequency BB. If you just get your calculator and you're getting the no base, it's not working right, hold the power button down until the square flashes, and then type in BB, Bravo, Bravo, and you'll be on the system. All right, so go ahead and vote for this question. You're riding on the UCF shuttle bus, but if it's crowded, you have to stand in the aisle, etc., etc. So what direction do you choose? 30 seconds. Ten, nine, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, we got 176 students. Wow. We should have about 50 more students clicking here. All right. I guess a few of the students floated away or something in the rain last time. Okay, you guys did good. 90% of you got this one correct. So if the bus accelerates forward, you're going to tend to, or if you've got fuzzy dice hanging from your rear view mirror, and you goose the accelerator forward, and the fuzzy dice are going to kind of swing backwards. So this is good. Now that's a pretty basic concept. Let's take a look at this one. All right, you're moving at constant velocity. Does that guarantee that no forces are acting on you? Read very carefully. As I say to one, I say to all. Read carefully. Da, 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 dum. Da, 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 dum. 20 seconds. Da, 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 dum. La, dum, da, dum, dum. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you... I see there's a lot of geniuses in here. All right? You know what? It's interesting. The first hour class, they were all over the place. This one, you've got 68% correct. They didn't even have 50% correct. They had 42% correct. So you guys are genius. This is the genius section, I guess. Either that or you talk to your classmates from the first hour. But the answer to this is D. And that is a case, or that is a concept for which this skydiver is an example. Terminal velocity. Raise your hand if you've ever done skydiving. Anybody? Okay, that's a pretty good number. Now, raise your hand if you've ever skydove without a static line. In other words, you jump out and you fall for a while and you get to pull the ripcord yourself. Raise your hand if you've done that. Nobody. So no, well, just you. Yeah, so in other words, the first time you jump, you got to jump with your instructor, and you're wired up to your instructor, I guess, or they pull it for you as you jump. But eventually you get to jump and then decide when to pull the ripcord, right? Yeah. So when you're skydiving, what happens is if you really are up there when you jump out of the airplane, and you just fall, and it must feel great. It must be really fun. No, it's not. You totally have a heart attack. Well, I mean, I'd have a heart attack getting out of the plane. But once you're out, why not enjoy it? At least until you reach the ground. Anyways, I don't know if I could do it, but if I did do it, I'd enjoy it. But if you do jump out of the plane and you get to pull your own ripcord, after a second or two, you're going to reach terminal velocity. Now, terminal velocity is a situation in which the downward pull of gravity is completely balanced by the upward push of air resistance. You know, if you're driving down to Miami on the turnpike and you roll the window down and put your hand out, you're going 65, you'll feel a little bit of push from the air going by the car. Now, if you're going, like 100 miles an hour or faster like a skydiver, you feel a lot of force. And eventually you're going so fast downward that the upward air resistance exactly balances the downward weight force. Now, the downward weight force, Omari, is the same all the way down. But as you accelerate, you get more and more upward air resistance until they exactly balance up and down. And then when they balance up and down, you stop accelerating. That's the terminal speed or terminal velocity. Colin. Yeah, Colin's saying if you change the shape of your body, the shape presented to the wind, basically. And the answer to that is yes. Just think of a sailboat. Sailboat trims its sails or puts up a jib or a spinnaker, depending on how fast they want, how the wind is going and stuff like that. And similarly, for a skydiver, if this guy's doing a belly flop, right? Pretty much. Okay, but if he were to tuck into a ball, bring his knees up and hug his knees, he'd start accelerating again. Okay, but he'd eventually get to terminal velocity, a different and higher terminal velocity. If he jumped feet first from the beginning, instead of jumping like this, whoa, excuse me, my microphone just did a belly flop. Hold on a second. If he went to the edge of the plane and just kind of stepped off and went straight down and kept his feet down, and then, he'd assume a terminal velocity. But then as soon as he did a belly flop, if turned himself, horizontal and took the belly flop position, he'd slow down. And because he's presenting so much sail area to the wind that it's giving him a lot, it'll slow him down. And then he'll assume a slower terminal speed in that case. And that's what a parachute does. A parachute effectively gives you more sail area that you present to the wind. It's above you. And so basically the area that you present to the wind is no longer as significant as the area that the parachute does. And so you pull the ripcord, your parachute comes out, and anybody that is with you and they don't pull the parachute, they just keep on going. So you pull the ripcord, and your buddy waits another second. He's looking at you up here like this. You're way up there because you seem to have slowed down as soon as your parachute grips the wind. Okay, so yeah, it's the amount of area that you present to the downward or to the upward flow of the wind of the air. It determines your terminal velocity. And so when you pop your parachute, your terminal velocity is now 5 miles an hour or whatever it happens to be. So that you don't totally kill yourself when you hit the ground. I mean, you can still break your ankle if you do it wrong, but I've seen, what was that show? That movie, San Andreas with The Rock, and he parachuted into the stadium. Well, some guy. So the stuntman parachuted into Candlestick Park in San Francisco. Anybody see that movie? Oh, you guys, man, I should make that a homework assignment. That was a cool movie. But anyway, so he parachutes in, and he just came in easy as light as a kitten. So depending on your parachute, you have different terminal speeds. But now, this is a kind of a nasty question, because if you look at this, and I can give you questions like this on a midterm or a final, no problem. There's 2 yeses, there's 2 nos, and there's 1 yes and no. So if somebody, tells you the answer is yes, 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 well, which one do you choose? And see, this is the kind of thing that you have to be able to handle. It's not enough just to say true or false, but you want to be able to be in the position where you can say why it is true, why it is false, why the answer is yes, why the answer is no. Now, this one, the answer is no, the second no, but the first no is horrible. And that is because forces are related to acceleration. Make a note of that. Option C is no good ski. No good ski is kind of a Polish term. Nogoodski. No good ski. After some Polish guy that was no good. Anyways, so this is no good. It's the worst. They definitely are related. All right. Now, I got another question for you, and it's going to be about this parabola, for which the launch velocity v subscript I, you better make a note of this, 10 meters per second, comma 19.8 meters per second. So its horizontal component of the initial velocity is 10 meters per second, 10.0 meters per second. And then the vertical component, it's going up, it's a positive 19.8. All right. That looks nice. Okay, so I got 19.8 meters per second going up at the start. Now that gives me a velocity vector initially that looks like this. All right, and that arrow, the tail of it is right at the, it's right here at the launch point. So this is where the baseball leaves the bat, if this were a home run heading for the outfield. All right, and it goes up. Now eventually the direction changes and the speeds change and everything, but initially that's its velocity. Now, what I want you to do, so here it is, just kind of this vector here. All right, so there's your initial velocity. Now, what I want you to focus on is the landing point. Okay, so the landing point's over here. And what I want you to answer to the best of your knowledge is, and I'll give you a chance to do this in just a second, what is the vertical component over here when it lands just before impact? All right, so go ahead and sketch your parabola. Sketch in your initial velocity vector here. Just try to do a good, job. If you're not another Leonardo da Vinci, that's all right. Just do your best. All right. And with your eye clicker, I want you to hit the refresh key because you're going to put a numeric answer in there. All right. And I'm going to give you the diagram back in just a second. So hit refresh. And when you hit refresh, you will get the number 1. And so what I want you to type in is the vertical component of velocity v subscript f just before impact. In other words, what's this number right here? Okay? Now, if you have to type in a negative number, go ahead. Negative 2.3 and give me your answer to the nearest tenth of a meter per second. All right? So go ahead and start. And as always, definitely talk it over with your neighbor if you feel like it. Because talking with a neighbor really helps sometimes. Question? What's that? What did I say? The what? That's 19.8 right here. Yeah, that 19.8 is the vertical component of the initial velocity. That's VIY. And this is the horizontal component, VIX. All right? Okay, 30 seconds. How are you supposed to what? There's no formula. You got to think. You're thinking like an engineer. What's the formula? That's what they do. They go look it up in the book. What's the formula I use for this? But what you really want to do is be able to think. Because it's actually a simple answer if you think carefully. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Get your answer in. Okay, I'm closing it this time. Wait a minute, where's my... All right, I'm really closing it. I really mean business this time. But let me see what you guys... Okay, 169 students. Well, it looks like we got a bunch of geniuses here because the answer is negative 19.8. Now, silencio. That's what my mom used to say when I was a little kid. If we were making too much noise, she would say silencio, and we know we were in big trouble. Now look at this. Look at these answers. Now, 62% of you got it correct. Good. Another 6% got 19.8. No, that is not wrong. That is not right. It is wrong. 19.8 is this. That's the initial velocity. The horizontal motion doesn't change. It's 10 and 10 both times, because there's no such thing as horizontal gravity, right? But what changes is the vertical component because of gravity. It loses 9.8 meters per second of upward speed, or gains 9.8 meters per second of downward speed for every second on the trajectory. Now, let me get my cursor back here for a second. All right. So this is your this is the final velocity vector, v subscript f. Go ahead and jot that in. Kind of draw that into your diagram. Right down here. Right here. All right. Now, it is comparable to v subscript I, the initial velocity. Now I'm going to move vi over so it's tail to tail with vf. All right, now watch, here it goes. All right, so there's vi tail to tail. Now it belongs back over here on the left, so let me bring it back over there. But you can see that they are mirror images. You know, one's up, one's down. And that is the effect of gravity. All right, now, final note, side note. For any path, no matter what the path, if it's straight or if it's curved, the velocity vector, that arrow, is always tangent to the path. So my arrows here just gracefully touch at one point only. That's what it means to be tangent. Okay? And just make it over that, no matter what curve we have for trajectory, the velocity vector, if you do want to try to draw it in, it has to be tangent. You know, so you could draw in a little tangent line and then the velocity vector based on that tangent line. Now, here's a picture from the internets of a home run trajectory. Now, this is a guy named Hunter Pence. He hit this home run out in Denver back in 2013, and 476 feet. Apparently, this is like a ginormous home run. It went all the way past the bleachers. Apparently, out here, it hit this brick wall behind the concession stand. This is a concession stand. All these people are out here buying hamburgers and hot dogs and stuff and whatnot. And so they're out there buying hot dogs and hamburgers. And meanwhile, Hunter Pence, he rocks one out there. And they got to dodge baseballs flying in from outer space. That is a monster home run. And on this trajectory, the vertical component of the motion is changing, but not the horizontal. Okay, so if you neglect air resistance, it's a perfect parabola. All right, in reality, it's a little bit less than a parabola, but it's pretty close. And so the question is, why is that? Why is Hunter Pence home run, his monster home run of 2013 at I guess that's Safeco Field out in Denver, or whatever the name of that baseball field is. It's a mile up in the atmosphere, Mile High City, Denver. And so the question is, why don't the horizontal components of the motion change? The velocity, that arrow is changing, right? There's the launch velocity, v subscript I. But the horizontal component of the velocity doesn't change. It's always 10 meters per second, all the way through. Or whatever it is. For him, it might have been 30 meters per second all the way through. I mean, that thing was a rocket. So what I'm going to ask you now is an alphanumeric question. I want you to hit the refresh key again. And I want you to build an answer, build an explanation for that question using this code table. And let me start the question for you. You should start, what do you have, A? The letter A? If you hit the refresh key, you should have the letter A. And here's your code table over here. Now, there's no French fries. There's no sharks. There's no leave Brittany alone. This is a regular physics question. And I could ask you a question like this on the midterm or the final. And I have done that on midterms and finals. So put together an answer. Why do the horizontal velocity components, why don't they change? Now, vertical, we know why that's changing, but why don't the horizontal? How would you write it? Now, think up an answer, and You might not have anybody else answering the exact same way that you do, and it might be perfectly correct. There might be 75 different correct answers in this class. Just depends on how you word it. All right, so put together, and put it in your notes as well. The question as well as your answer. Okay? Now, if you spell your name, I'm going to know it. So don't write Jonathan or whatever your first name is. But do try to put together a good explanation. I hear those clickers clicking. And definitely talk with your neighbor. Talk it over. See what they think. If you have somebody that you're sitting with. And if you're sitting next to Darien, you could talk it over with Darien. Yo, front row. Young lady with the white shirt, the white top. You're sitting next to Darien. So she knows all the way through all this stuff. So don't be shy about talking to her or to anybody. It's really good. I see you guys trying to point to different things, and it's good. Yeah, you might have a question like this on midterm 1 a week from today. I can't tell you what's going to be on the test, but if you think about this one, you might be happy next Thursday afternoon. One minute. Don't forget to hit the send key. Ten, 9, 8, 7, 6, 4. Wait a minute. I was looking at the numbers here. Okay. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Slackers, get that thing clicked in. Come on, one more. We're at 175. You know who you... All right, there we go. All right, now let's see what you guys have got. Whoa. You know, this is kind of interesting. SZQ, look at that. Only 7 people typed in that answer. Now, I'm not saying it's correct, but it's the most popular answer. Let's see if it's correct. SZQ. Force never change. Force never changes. That is partially correct. The gravitational force is always down, but that one would only be partial credit because you would want to mention that the force is downward. The gravitational force is downward and never changes. So that one's partially okay. CZQ. Let's look at this one. CZQ. Directions never change. Incorrect. CZQ, Charlie, Zulu, Quebec, is incorrect. The direction of the baseball definitely changes. You know, it's going this way on the way up, and it's going this way on the way down. That's a change. Let's look at a couple more here. NVZOG. November, Victor, Zulu, Oscar, Golf. Let's see. That's this one. NVZOG. Okay, NV, horizontal position, no, horizontal velocity. NVZ never has G. No. NVZOG is incorrect. That's mixing apples and oranges. I could see where if you now I'm not, you know, don't make a mistake. If you voted for that or if that was your answer, I'm not making fun of you. I'm trying to talk about the things that I see. I don't know who it is. I won't know until later when I analyze the spreadsheets, but let's look at one more. Let's go way down here. Whoa, here's a long one. NVLK BEOPQ. Whoa, let's see what that one is. Okay, NV, horizontal velocity, NVLK. Horizontal velocity from up. Whoa, that's no good. BEOPQ. And has, no, BEOPQ. And down, up and down has PQ. Not changed. That's kind of a mix. I'd have to look at that one carefully. Let's look at one more here. All right, let's look at this one. One student voted for NVZOA. Horizontal velocity never has acceleration. Whoa! Whoever did that, you are right on the money. I'm not going to look for a show of hands, but and I know, don't everybody put up their hand because I know it's only one person. This tells me, I'm going to show it to you. Hold on a second. This tells me only one person voted for NVZOA, but that is a crackerjack answer. So whoever answered that, you can tell me on email tonight in web courses. That is, well, I'll know anyways as soon as I grade this. That's a lovely answer. So I'll probably give you some more. I'll analyze all of them tonight and grade them. And it's just 1 point or 0. And then over the weekend I'll post those. And then Tuesday we'll go over some more of the nice answers. And just to reinforce, do expect to see a question, at least one question like this on the midterm next week. All right, let's talk about the 3 laws of motions. We're going to take some notes, and we got one more clicker question coming. So don't put your clicker away. Now, Galileo's whole thing about defeating Aristotle using ramps, that there's no minimum force. The minimum is 0. That's all you need on a frictionless horizontal plane to keep in motion, because the object in motion is indifferent to rest or velocity. being in motion or being at rest. Sir Isaac Newton wrote it down approximately this way. Every object retains its state of rest or its state of uniform straight line motion, in other words, constant velocity, unless acted upon by an unbalanced force. And that is basically his first law, and but it was developed by Galileo. And Sir Isaac Newton was famous for saying, "If I have seen far, it is because I stood on the shoulders of giants." He stood on the shoulders of Galileo and Kepler. Now, here's an example of the first law in the manner that Sir Isaac Newton intended. Apple in an apple tree, balanced forces. All right? If you think about an apple in an apple tree, it's attached to the stem of the stem of the apple is attached to the branch, and it's got some tensile strength, and so that stem produces some upward tensile force on the apple, and it balances completely with the downward weight force, the gravitational weight force, which is down. And if it does balance, the apple stays at rest. It stays on the branch. But if you have a fruit tree in your backyard or your parents' backyard, or anywhere you may go around here in Florida, there's orange trees all over the place, grapefruit trees, tangerine trees. You know that the fruit eventually falls to the ground. Well, when that happens, the stem weakens. It dries out eventually, and it loses a little bit of its tensile strength. The balance will fail, and down it goes. Okay, and if you're Sir Isaac Newton taking a snooze under the apple tree, it'll fall on your coconut. And that's how they say that he started thinking about gravity and universal gravitation. It's one of those legends that he never really, he must have told somebody, but nobody's been able to 100% verify that actually happened. Just like with Professor Galileo and the Leaning Tower of Pisa, everybody thinks it happened, but he never really said, "Yep, definitely, I did it on such and such a date." So it's a legend that everybody believes in. Kind of like Tom Brady is a good guy. That's a legend that everybody believes in. Don't get me started on that. Okay, anyways, here's another example, Newton's first law. And let's think in terms of a bus, UCF shuttle bus. And everybody in here is probably taking the shuttle bus, or most of you anyways, from time to time. Okay, if the bus moves forward, you're going to lurch backward. We talked about that in one of the clicker questions. Okay, and that's because you tend, if you're not bolted down to the bus, you're going to want to stay in your original state of motion. So if it speeds up, it's like speeding up below you. And if it speeds up forward, your feet are going to go forward. Your feet are kind of attached to the bus, but the rest of you is going to, tilt backwards. So you got to steady yourself. Right? Similarly, if the bus turns to the right, you're going to want to keep going straight, and that feels like you're going to bump your left side into one of the seats or into your neighbor on your left. All right? So left and right, forward and aft, those are separate motions, and that's why they have all those bars and braces and stuff on the shuttle bus. Even the seats have little handles that you can grab a hold of for safety. All right? And you usually use that unless your bus never changes its state of motion. But here at UCF, I don't know, those guys seem to drive like maniacs. Anybody ever notice that? They just drive like they go really fast and they slow down and they go really fast again. I don't know. You get car sick with those guys. All right, so those are separate interactions. Same thing with this baseball if you think about it. Here's Here's the picture of this home run out in Denver. And it's got separable motions, the vertical component and the horizontal component. The horizontal component is unchanging, but the vertical component is definitely changing all at every instant. So on the bus, forward and aft, starboard and port, up and down. You know, if you hit a pothole, you're going down, you're going up. On the way out of the pothole, yeah, those are separable motions. So we have to keep track of those stuff. And so if you, the bottom line is you're gonna, whatever state of motion you're in, you're gonna tend to stay in that state of motion. You know, and if you get jostled left to right, or if you get jostled forward or back, or up and down, you know, you're gonna feel it. Okay. Now, if you're not in a constant state of motion, that's because of an unbalanced force. And so, just like, you know, this transformer here, this is one of my favorite transformers, Jetfire. His father was a wheel, the first wheel. And you know, Jetfire was, you know, got these guys over to Egypt and everything, all their adventures, and he really got them in a state of motion. So let's talk about the states of motion for unbalanced forces. Now this is where Newton's second law comes in. This is the heart of his whole system of analyzing motion, because this is the one that allows you to generate an equation of motion, or a time evolution equation, as we say, and predict future states of motion if you have enough initial information. Okay, so here's the first thing he did. He said, all right, add up all your forces, and if anything doesn't balance, then that's the net force. Okay? So as an example, let's think about Dwight Howard and LeBron James. Okay, if LeBron James, let me get my cursor over here. If LeBron James is pulling to the left and Dwight Howard is pulling to the right, you know, one of them is going to be stronger. So in this example, let's say that Dwight Howard is pulling to the right with 100 generic units of force, and that LeBron James is pulling to the left with 80 generic units of force. All right, so he's pulling leftward, so we give him the number -80. Right? Now, Dwight Howard is 20 units stronger, and that means that the net force is 20 units of force, positive or rightward. And so that's this arrow right down here. Okay, so between those two guys, they don't perfectly balance, and whoever has more pull, that's where the net force is going to point towards that guy. In this case, Dwight Howard. Now, another concept that Sir Isaac Newton said was figure out how much push force you've got. Figure out your net, and then if you have more net force, you're going to get more acceleration. All right? Now, here's a colloquial example for that. Think of Arnold Schwarzenegger pushing a grocery cart, a loaded grocery cart at Publix, versus a little kindergartner pushing the same cart. Okay, the little kindergartner is going to accelerate it, but it's going to be kind of pokey. But Arnold's going to really jam it. He's going to really give it some good acceleration. All right? Because he has more push force. Third thing, if the shopping cart has more kilograms, if you load the shopping cart, like if you load it with water's pretty heavy, versus loading it with the same volume of Cheerios, boxes of Cheerios, or ramen noodles, that's really light. Okay? Raise your hand if you've had ramen noodles for dinner last night. I know, man, it's pathetic. I know, I like them too, but sometimes that's the only thing you have. Anyway, so if you load up your cart with ramen noodles, no matter who you are, you're going to accelerate it at a higher acceleration than if you load it with the same volume of water, because water is more dense. Water is 1 kilogram for every liter. Ramen noodle is like about 1 gram for every cubic liter. So now he put it together into this mathematical formula, and hopefully this makes sense to you. The acceleration is the quotient of the net force divided by the mass. All right? The net force is in the numerator. Okay? More net force, more acceleration. The mass is in the denominator. So if you have more kilograms of mass, that's in the denominator now. You have a smaller quotient, so not as much acceleration. And this is his simple law. F net over m equals acceleration a. Here's another way that it is written in a little more compact way. We're in the engineering building, Harris Engineering. If you go out there in the hallway and interview 10 engineering students and ask them, well, what's Newton's second law? This is the one that they'll say. F equals ma. Okay? It's equivalent. It's just a different way of writing. It's a little more compact. Okay, so F equals ma, A equals F net over m. Those are Newton's second law. Now, a couple things about it. I want to go a little bit deeper into it. And we have one more clicker question coming up. So, and actually, you know what? Let's skip ahead. Let's see if I can